Assalamualaikum and a very good morning to our lecturer, Dr. Mu'in. My name is Muhammad Asnizal bin Asmani and my matric number is MA19213 and I from group 5. My group member is RAHIMAN bin RASHID, Muhammad FILZA bin MAZLAN Long, HAIKAL HAKIM bin NAZRI and one Nur ASHIKIN BINTI one UMAR BAKI. Okay, now I would like to present about chapter 1 introduction. Okay, first is background. The application of Bernoulli principle to determining the flow speed of a fluid is another example. To reduce the diameter of the flow, devices such as a venturimeter or an orifice plate are utilized and can be put into a pipeline. Due to the rise in fluid flow speed caused by the reduction in diameter, Bernoulli Law dictates that pressure must decrease. As the speed of a moving fluid, which is liquid or gas, increase, the pressure within the fluid falls, write Daniel Bernoulli in his book. In 1738, he developed this idea and published it in his book Hydrodynamica. The book explained the hydrodynamic pressure by describing the principle of water flowing through a tube and water flowing from a hole in a container. Okay. Next is the problem statement. In this experiment, we can know how to determine a steady, continuous, incompressible, and non non-viscous fluid flow. The total energy or total heat remains constant at all the sections along the fluid flows, provided there is no loss or addition of energy. The total pressure is measured using the pitot tube on the right side of the instrument. The multi-tube manometer at the top of the equipment is used to measure the static heat. Is it possible to adjust the static and dynamic heat of the fluid flow through a volumetric tank using a venturi apparatus? Next is objective. First, to determine total pressure heat of the fluid flow through volumetric tank. And the second objective is to analyze the fluid flow through a volumetric tank, static heat. And lastly is to calculate the dynamic heat of a fluid flow in a volumetric tank. Okay, next is 1.4, which is scope. First, at the top of the equipment, a multi-tube manometer is used to measure the static heat. Second, to look into the overall pressure head, static head, and dynamic load variation. And last but not least is to calculate the fluid velocity through the volumetric tank and the dynamic head. Right, that's all from me, and I will pass to my friend to explain their part. Thank you.
Thank you to my teammates. My name is Wanur Ashikin Binti Wan Umar Baki, matrix number MA19216. So I'll be explaining on the Bernoulli's principle. According to Bernoulli's principle, the pressure of the liquid flow decreases with increasing flow speed. This principle is based on the ideal law of conservation of energy in fluids. When a liquid flow in a horizontal motion, where the potential gravitational energy of liquid does not change, increasing the speed of liquid will reduce the pressure of the liquid and vice versa. Therefore, in an ideal incompressible fluid with a stable and continuous flow, the total energy of potential, kinetic, and pressure energy is constant along the streamline. So in short, Bernoulli's equation is derived under the following assumption. First, fluid is incompressible, flow is steady, flow is frictionless, and along a streamline. The Bernoulli's equation can be expressed as P over rho g plus V square over 2g plus z is equal to constant, where P over rho g is the static head, V square over 2g is the velocity head, and z is the elevation. So the sum of pressure head, velocity head, and the elevation head is known as the total head. The total head at any cross-section is constant according to Bernoulli's principle. And since the center lines of all cross-sections are assumed to be on the same horizontal plane, all z values are 0. So the above equation is P over rho g plus V square over 2g is equal to H is equal to constant. So this is the equation that can be used to represent the total head at the cross-section. So that's all from me. Thank you.
My name is RAHIMAN bin Rashid. I will presenting Chapter 3 Methodology and Procedure. Introduction. An experiment was carried out in order to achieve the experiment objective. Liberation of the total pressure head, static head, and dynamic head were investigated in this experiment. The total pressure is measured using the pitot tube on the right side of the instrument. The multi-tube manometer at the top of the equipment is used to measure the static head. Below are the two methods and procedure involved in conducting this experiment. First, methodology. The experiment compares practical and theoretical data to test if Bernoulli's principle is true, stating that when a fluid flows at velocity, the pressure surrounding the fluid decreases. This equation is approximation of the pressure, velocity, and elevation relationship. It is also true in region of steady, incompressible flow with zero net gravitational forces. As a result, a comparison of experiment and theoretical method is applied. The procedure for the experiment: 1. Vent valve, 1. Control valve, manometer valve, and single pitot manometer valve are fully open. 2. The vent valve tube is half open. 3. The water pump switch is turned on so that the water is allowed to overflow both the manometer valve to expel air bubble from the manometers. 4. The manometer valve and single pitot manometer valve are closed. 5. The pump is stopped and the vent valve 2 is closed simultaneously while vent valve 1 remains fully open. 6. The manometer valve and single pitot manometer valve is opened carefully to allow atmospheric air to get in and close both valves when the water reaches about half of the column. 7. The manometer valve and single pitot manometer valve is reopened and the pump is switched on. 8. When valve 2 is fully open and the control valve is adjusted so that the position that all the water level in manometers are readable. 9. The static head and the pitot head for all the 6 positions in the venturi tube is read and recorded by adjusting the pitot probe to the desired position 1 to 6. 10. The static head and pitot head reading is recorded and tabulated. 11. The flow rate is determined by the time required to raise the water tank by 5 liters using the stopwatch, and the time taken is recorded. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is HAIKAL HAKIM NAZRI. So I will continue this presentation with the results and discussion. This is the inner diameter, the data of inner diameter that has been provided to us. So when we have the inner diameter, so we can calculate the area. So to calculate the area, we use the formula of area equals to pi r square. And this is the sample calculation of the area. Next, calculation of flow rate. The calculation of flow rate, we use the formula of flow rate, or Q, equals to V over T, as we have been given V equals to 5 liter and T equals to 25 seconds. So we divided these two things, then we get the flow rate, which is 0.2 meter cube per second. Next is this is the data of the static head, and this is the graph of the static head, and also this is the data of pitot head, and this is the graph of the pitot head that has been done by using Microsoft Excel. Okay, next let's we move on to the calculation. So after we have calculated the Q and A, so we can get the velocity. So to calculate the velocity, we use the formula of Q divided by A equals to V, and this is the sample calculation of the velocity. After that, calculation of pressure. So to calculate the pressure, we use the formula of rho Vg divided by A equals to P, which is rho is the density of water, V is the volume, and G is the gravity, whilst A is the area. So this is the answer that we get for the pressure. Next, the calculation of pressure head. To calculate the pressure head, we use the formula of P equals to P divided by rho G, which is pressure divided by density of water times gravity, and this is the answer that we get for the pressure head. Next is the velocity head. To calculate the velocity head, we use the formula of V power of 2 divided by 2G. So this is the sample calculation of velocity head. And the last one is the calculation of total head. After we get the answer for velocity head and answer for pressure head, we just added these two things and then we can get the total head. So this is the sample calculation for the total head. Next is this is the all calculation that has been made for this Bernoulli's principle lab from point 1 to point 6. So we can look the answer here. Okay. Next, we go to discussion. Of course, the objective of this lab is to see if Bernoulli's principle holds true in a tapering duct with a steady flow water. A practical application of Bernoulli's principle is the Venturi tube. The Venturi tube has an inlet that narrows to a throat, constricted point, and an outlet section that increases in diameter toward the rear. According to the findings, when the diameter of the Venturi is reduced, the pressure rises and the velocity rises as well. As we can see early, when the inner diameter becomes smaller, then the pressure and the velocity becomes higher. So that's what it said. For the overall, the data and graph obtained from this experiment, it is verified the Bernoulli's principle. That's all from me. Thank you very much.
Hi, Assalamualaikum. To my fellow classmate and lecturer, my name is Muhammad FILZA bin MAZLAN Law. My metric number is MA19208. So now I will continue this slide presentation for the conclusion part. In conclusion, this experiment is to measure the variation in total pressure head, static pressure, and dynamic head. At all 6 data collecting sites, there was a strong correlation between pitot total head reading and static head reading. The difference between the pitot total head and the static head readings influenced the change of dynamic head. As the liquid level in the tank decreases, the vertical increment rises, increasing the total dynamic head. And as a result, it is possible to calculate the difference between the total pressure head and the static head. The dynamic head losses are usually caused by friction losses that occur in the system. The difference between pipe fittings, junctions, converging and diverging tubes, turns, and the pipe surface roughness are the cause of dynamic head losses in a piping system. So we can conclude from this experiment that the overall pressure head is mainly controlled by its velocity and the fluid pressure drops as the flow velocity increases. So this is the reference that our group used to finish this report. So I think that's all from me. So thank you.